Hello children, let me explain how current loop acts as a magnetic dipole. Okay, for that let me explain a bar magnet. And a bar magnet has two poles, north pole and south pole. Therefore, it is a magnetic dipole. Okay. Similarly, a current loop. See, current is flowing anticlockwise. If we see it from the top, the current is flowing in anticlockwise. If the current is flowing anticlockwise, then this current will produce magnetic field, and this side, the top side, will be north pole. But if you see this loop from the top, it is looking that current is flowing anticlockwise. If we see it from the bottom, then the same current will flow in the clockwise direction. So from the bottom, if you see this loop, this pole will be the south pole. Therefore, this current carrying loop acts like a bar magnet having two poles, north pole and south pole. Therefore, this current carrying loop is also act as a magnetic dipole. Okay, just like a bar magnet has two poles, north and south pole, therefore it is a magnetic dipole. Similarly, a current carrying loop is a magnetic dipole because it has two poles, north pole and south pole, depending upon the direction of the current. If the direction of the current is anticlockwise from the top, it will be north pole, and the same anticlockwise direction, if you see it from the bottom, it will look like the current is flowing clockwise. Therefore, the bottom side will be the south pole, and this north and south pole forms a magnetic dipole. Therefore, current carrying loop as a magnetic dipole. Now we want to measure this magnetic dipole. What is the value of this magnetic dipole? What is the formula of magnetic dipole? We know that if we have a current carrying loop, if you place it in a magnetic field, then it will experience torque. Okay. If you have a current carrying loop, okay, if you place it in between the magnets, then it will experience a torque. That torque is this formula, tau equals to IAB sine theta. Similarly, if we have a current carrying loop, if you have a similarly, we know this formula, no, that torque experienced by an electric dipole. If you have electric dipole in a uniform electric field, if you have an electric dipole in a uniform electric field, then it will experience a torque which is equals to P sine theta again. So this is a torque experience in the magnetic field. This is a torque experience in the electric field. Here P is the electric dipole moment, is the electric field. So you can see this is in the magnetic field, therefore B sine theta. This is in the electric field, therefore E sine theta. And this is electric dipole moment. So if you compare this and this, then P should be equal to IA. So IA has to be magnetic dipole moment. If tau is the torque in the electric field, then this is electric dipole moment. If tau is the torque in the magnetic field, then this has to be the magnetic dipole moment, because the other two are comparable, they are same. Okay, therefore we got magnetic dipole moment equals to M equals to I into A. Okay, this is a vector quantity, and M vector equals to IA vector. So this is a formula for magnetic dipole moment.